Welcome learners to this new lecture series on the course of Electromagnetic Field Theory. I am your instructor for this lecture series, Dr. Waleed Tariq Sethi. And now let us see what this course is all about. So in this course, we are going to unlock the invisible forces shaping the world around us. Imagine every time you use your phone, you stream a video, or even if you enter a room and turn on a light, you are basically tapping into the power of electric and magnetic field. These fields aren't just abstract concepts, they are the backbone of modern technology, from wireless communication to medical imaging to using electric vehicles and even the GPS that gets you to class on time. So the question is that what are we going to learn, or what is the outcome if we learn this course? So once you have learned this course, you have different tracks to follow. The first being the purpose of learning this course, EMT, is first and foremost is basically we are going to understand the fundamental rules of nature, or you can say we can understand how the universe communicates with us. And this is governed by understanding at the atomic level the charges that exist, and these charges used to generate the currents or the time varying currents, or basically how these currents interact with each other. So this is the fundamental idea. And how do we deal with these currents that are varying with time? We use the four elegant equations given by Maxwell. So the main objective, or the second objective of this course, other than understanding the fundamental rules of nature, is to understand how the Maxwell's equation govern the possibility of electricity and magnetism working hand in hand. So this is the second objective. And finally, we basically utilize all these things to decode what the nature has given us. So we basically want to decode the nature when we interact the natural phenomena with the man-made technological devices or the electronic devices being utilized. So all these things that govern or shape the modern world, or the applications where the electric and magnetic field combine together, are utilized, and we are going to understand all these things in this course of electromagnetic fields theory. But again, it is not the theoretical concept. We basically want to understand in any course what is going to be the outcome of it. So from the outcome that we can govern is you can take three paths as a career along with many other options. But the three basic are that once you learn this course and learn its practical applications, you can pursue your career as an engineer, where you can use the knowledge gained to design different antennas for wireless communication. You can work on different transmission lines. As an embedded engineer, you can work on interconnect or interconnections as we call them. You can also work on making renewable energy accessible and more efficient when we talk about photons being presented in the sunlight. If you don't aspire to become an engineer, you can go to the field of science and physicist, where you can basically understand how the wireless or Wi-Fi signals are generated, what is the fundamental knowledge behind laser technology, and how the radar basically works. And if you don't want to go into these things, you can become an astrophysics, or you can work on the simulation aspect of things, where nowadays the current technology is on quantum computing. So you can use different simulation models which are based on the computational electromagnetics provided by this course, and then you can uncover the forces that shape our modern world. So these are basically the career paths or the outcomes that you can learn from this course. So now let us look at the basic things needed to learn about this course. So as always, we are going to stick to a main textbook. For this course, we are going to use the 9th edition of Engineering Electromagnetics course written by William Haight and John A. Buck. This edition was launched in 2019. And to add more to your knowledge, we are going to follow these three reference books. The first is Elements of Electromagnetics, a very basic understanding of concepts is presented in these books written by Sadiku and Nelachari. Then we can also look into book, an old one, but a more in-depth by David Cheng, released in 1989. And if you want to understand the practical aspects or the applied electromagnetics, you can look into the book by Fawaz Alabey, Fundamentals of Applied Electromagnetics, and this is the 2014 version of it. So these are the books that is going to help us understand various concepts in the field of electromagnetic theory. So now let us jump into this course, this exciting course, as I say, and look to the world through the lens of electromagnetism. So the first thing that comes to our mind whenever we study about anything is, what is that thing? In our case, we want to understand what is electromagnetic field theory. To put it simple, this course is going to help us understand three things. The first thing is, what is a field? So what is a field? Whether if it is electric or magnetic, so how do we comprehend these fields which we cannot visually see but can virtually simulate or understand its working principle? The next question that comes in mind is how these fields are generated. So how the fields are generated. And the third thing that we are going to understand by the end of this course is that how these fields interact with each other. So how these fields interact with each other. So these are the broader questions that we are going to have an answer by the end of this course or interesting course of electromagnetic field theory. So let us look into the basic definitions of electromagnetic field theory. So as I mentioned that most of the engineering courses are derived from mathematics and physics. So this course of electromagnetic field theory is basically derived as a branch of physics where we study the interaction between electric and magnetic fields. So this is what we are going to do. Second, we are going to understand at the atomic level that how the charges with which in turn generates the currents are going to produce, and how these forces are going to affect each other if, let's say, one charge is present and we introduce another charge in its vicinity. So how these charges are going to interact with each other. How is the current going to be flowing from one charge to the other and vice versa. And we are also going to look at some of the practical examples where these electric and magnetic waves combine, which we call as an electromagnetic wave. So electromagnetic wave is when we combine electric and magnetic fields together. So here we are represented as an electric and magnetic vector. So these applications include the light that we see, the radio waves, microwaves, X-rays, and how these waves are propagated in free space. So this is what the electromagnetic field is all about, or this is what we are going to learn in this course. So a few examples where we have seen these electromagnetism working hand in hand, and obviously you must have seen microwaves in your homes which generate these electromagnetic waves. We use this to heat any given cold food or defrost most of the foods. Again, those sources which generate an electric and magnetic effect, we term them as an electromagnetic device or electromagnetic generating device. Similarly, our cellular communications are made possible by these gigantic GSM towers. So again, they are example of an electromagnetic wave. The light waves that we have are also example of electromagnetic wave. In some of the courses, we consider or compare waves to photons. So these are the two school of thoughts, the Newtonian and the Einstein, but again the idea is the same, that they are generating something coming out in the form of waves. So for the electric bulb, it is the light waves. we may have seen, or you may have seen in your physics classes, the use of prism, that it can concentrate and diverge or converge light waves into inlets and outlets. So if we have multiple sources entering or a light spectrum, all these are combined into a white light or a white spectrum. So this is the example of a prism. On the other hand, X-rays is something that for the medical purposes we again use electromagnetic waves combined together to look into the human body, especially the bones structure. Then we have MRI and CT scan machines, again using the gamma rays and the ultraviolet rays to do the analysis. Charges and magnetics are also a part of the electromagnetic waves, but they don't propagate, they are the static version of it. So something that is still and not moving, so we say these are the static charges and magnetic fields. So these are some of the broader examples of where the electromagnetic fields are seen in action in day-to-day life. Another thing that is not to be confused with electromagnetic is the sound waves. Again, they are not being generated by an electric and magnetic source, rather they are generated by the natural chords in the human voice. So these are the sound waves, the ones you hear on your speakers. So they are artificially generated or using other mediums to generate through the megaphone. Then there are gravitational vibrations that cannot be considered as electromagnetic waves. So gravity is something that still people are researching upon. We know that something exists in gravity, but we haven't come to a conclusion that why it is happening or what are the forces that govern it. We do have Newtonian principles on it, but again it is not an electromagnetic source, it is a separate entity. So all these examples are just to show you what can be considered as an electromagnetic source and what is not an electromagnetic source. So moving on, we can summarize that anything which is associated with the charges at the atomic level, if it is an electric charge, like a positive charge we call as proton, or a negative charge we call as an electron, and if they are involved, whether they are in static or in motion, we say that this is a source of an electric field, and thus it is a part of an electromagnetism. Similarly, magnetic fields, if there exists a north and south pole and the waves are generating from the north and moving towards the south, so we say that this is the source of a magnetic field and it can become a part of an electromagnetic wave. We can visualize the fields as well. So here you can see if we have a proton and we have an electron, so we can see that if the distance between charges are less, so the waves are moving in a straight line, but if the distance is increased, so we can see they are following a spiral path over here. So this is an animation where we can see how the electric fields are being visualized. Similarly, we can also look towards a magnetic field. So if we have a magnetic bar, we can see this is a spiral or a cylindrical motion. Later on we'll see that it is the waves are moving from the north towards the south pole. So this is a realistic visualization of the magnetic field surrounding a bar magnet. So when we combine these two waves together, we get something known as an electromagnetic wave, and we will see later on that if this is an electric field shown in blue and 90-degree apart is the magnetic field shown in H, so the wave is propagating in the perpendicular direction to it. So this is how the electric and magnetic field is basically operating, and we call this as an EM wave. So we are going to study that how these waves are basically moving from the E field to the magnet field, and this is an example where we can see even in nature that the electric and magnetic fields can be in the form of the dense smog that we see, or the fog in the winter season, where sunlight rays are getting deflected or reflected from the surface of the earth. So we see just a portion of one wave. In this case it is something like an electric wave that is moving. So all these are the practical visual examples of how the waves in nature can be visualized. So now we come to something that is very widely used in electromagnetic, and that is an electromagnetic visual spectrum. So electromagnetic spectrum basically gives us an idea about the relationship between frequency and wavelength, which is normally C equals to F lambda, or we can say that F is equals to C by lambda. So if the frequency is getting increased, the wavelength on the other hand is getting decreased. So it's an inverse relationship that we normally see in this spectrum. So what we can see is that if we talk about the radio waves, you can see that the frequency is very low, represented this by this line, but the wavelength is in the order of 10 raised to power 3, which can mostly cover very wider buildings. So that's why we can say that the frequency signals that we use in our AM and FM radio stations, normally if we talk about FM signals, so they range from 89 megahertz in some parts of the world, and it can go to like 108 megahertz. So the frequency is in the power of megahertz, which is 10 raised to power 6 hertz. So you can see that the wavelength is huge compared to the frequency, so it can be normally the size of a very wide building. But if you increase the frequency to microwaves, that is normally in the gigahertz, 10 raised to power 9, you can see that the wavelength is now becoming smaller, 10 raised to minus 12. So the wavelength is such that it can cover the complete ball from the baseball. Similarly, if you increase the infrared frequency, you can see the size of the wavelength is getting smaller and the frequency. So we can say that in this spectrum, the frequency is increasing as we move towards the right side and the wavelength is decreasing. Even if you go to the visible light, which normally falls in the 400 to 700 nanometer or the wavelength spectrum, you can see the size is smaller to that of a bacteria, that is 5 × 10 to the power minus 6 or 5 micrometer. Similarly, ultraviolet, the frequency is increasing. You can see the frequency being formed, the wavelength is getting smaller. X-rays, the frequency is increasing. Gamma, the frequency has been increased or compressed so much that the wavelength is now in the nanometer or picometer scale, so 10 raised to power minus 9 and beyond. So this is just to show you the relationship between frequency and wavelength, and obviously the advantage is that if the wavelength is more, it can travel farther distances. For example, in the case of AM and FM signals, or even in the GSM towers, where we have the range from 980 megahertz to around 2.45 gigahertz. So this is the range where most of the cellular communication happens. If we are using Wi-Fi signals, then we can go to 5.8 gigahertz as well. But these frequencies have their applications and advances in terms of the wavelength. So if we are in the megahertz band, the wave can travel farther. If we are in the cellular communication, then the traveling of the wavelength becomes small, or the wave is traveled at a certain distance. Then we use repeaters to enhance the wave's amplitude and then retransmit again, or these are called repeaters as well. So again, these are the things that we will study later on, but our focus will be how to generate initially the electric and magnetic wave, and this is an example of the electromagnetic spectrum. So now coming to a very important comparison of the electromagnetic field theory with the circuit theory course that you might have studied in your earlier semester, or sometimes it is known as linear circuit analysis. So we want to understand that what is the comparison between the electromagnetic field theory, our topic of interest, and what we have studied previously, that is the circuit analysis courses or the basic circuit theory. So before we look into this example, we need to understand what we studied in the previous circuit analysis course. So in the circuit analysis course, so let me say the circuit theory course, if you remember, we said that circuit theory course is an extraction or a specialized version of the electromagnetic fields theory course. And how do we make this an extraction or a specialized version? So we considered certain rules when we were studying the circuit theory course. So what were the rules? So the rules were such that for the circuit theory course, we assumed that the components were lumped nature, or we said they were lumped elements. Lumped elements means that the physical size of the object the object being the passive elements, inductor, resistor and capacitor, not the sources at this moment. So the physical size of the elements were small compared to the wavelength, of the signal. So which meant that we can assume that whatever the signal was passing through these elements RLC, they were having a instantaneous effect. So the instantaneous effect, what does it mean? So it means like if I take a resistor value of R and I say its value is 10 ohms. So if we are taking this or considering this to be a lumped component, we assume that whatever the energy was input at the terminal A, the same energy is received at the output terminal B, which is 10 ohms, because we are considering that the wavelength. So if I can change the pointer. So we are assuming that the wavelength is so large that it is covering the entire element, which means that the input and output will have the same effect across the resistor. If we haven't or if we didn't assume the lump component, then the behavior of resistors energy from point A to point B would be in partitions. So here the energy would be, let's say 1 ohm, here it would be 1.5 and so on and so forth. So if it hadn't been a lumped component, then the resistors would have been separated into different sections and the output may not be an equal 10 ohm, rather different or reduced version, maybe 9.95 ohm or 8 ohm at the output. But since we assumed it to be a lumped component, we said that it is going to have an instantaneous or across the board its value will be the same. So we said it is going to be a complete 10 ohm. So this was the first assumption we took in the circuit theory course. The second assumption we took was that the net charge on every element would be 0. So whatever the amount of energy enters, the same amount of energy should be leaving the component. We had few exceptions in the case of inductors and capacitor, that they were a temporary storing device, but again they would also release the energy which was stored. So the net charge or the net energy was 0 on every component. And the final postulate that we considered was that the magnetic effect on the elements would not be considered or it would be ignored. So these were the three postulates or the rules that we utilize. Now these three rules cannot be applied to practical applications. And for example, if we are talking about any PCB board, so this is a printed circuit board and we say that it has some transistor component installed, it has some diode installed over here, and we make certain interconnections between them. So now the problem is, if we are trying to understand how the signals or voltages or currents are moving inside these transmission lines in the form of signals or waves or in the form of plus minus waves, we cannot neglect the electric and magnetic effect, or what we called as a coupling behavior when we are dealing with practical circuits, like a circuit made on a printed circuit board. So this means that the basic postulates, the three ones over here which we assumed for circuit analysis, cannot be applied on this PCB because the coupling effect is going to exist between the elements. So if we have one transistor over here and a diode over here, there is going to be some electric which is going to result in a magnetic effect between these two elements. And if this magnetic effect exists, which means our logic of circuit theory is not going to be applied, we need to come up with a new technique that can help us solve these problems or troubleshoot these problems which is existing in any practical circuit board. Hence, we say that in order to overcome these limitations of circuit theory, we need to revisit the electromagnetic field theory that provides the answer to these problems which arise in practical circuits. So we can say this is the reason that we want to move from the basic circuit theory to a advanced course or the standardized code of electromagnetic field theory. So let us better understand these limitations of circuit theory and how EMT is going to help us understand these limitations or provide a solution to these limitations. So we begin with the first basic circuit and first limitations and the advantages provided to us by the EMT course. So let us say we have been given this basic circuit where we have an AC voltage source. We have a switch over here, and at time is equal to 0 the switch is going to be closed. Before that it is going to open, and this is an incomplete circuit. So the circuit is incomplete because the loop is not closed. Loop is not closed. So the circuit is not complete. We can see the terminals are open at this end. Now if we look at this circuit and we do the analysis from the circuit's perspective, we see that there can be two outcomes for this circuit, and the two outcomes are presented in the yellow highlights. So either it can be option A or it can be option E. What this means is, if we look at this circuit from a circuits engineer perspective, we get two options. What are the two options? The two options is that if this is a voltage source, it is going to generate a current. The current is going to flow when the switch is closed at time equals to 0. So we can see that at the end of this circuit, the terminals are open. So this is an open circuit. If the terminals are open, this means that the current is going to be 0 amps because the path is not complete over here. So the current has no path to flow. So we can say from the knowledge of the circuit theory that the current for this circuit at the output terminals, this point, is going to be 0 amps. This is fine. What other piece of information we get? If we look at this as a circuits engineer perspective, we see since this is an open circuit, the output voltage or the load voltage that we are going to have is going to be the same which is available at the AC source. So the output voltage V out is going to be the same which is the voltage available at the source. So this is fine. So if we are in the circuits theory domain, the analysis is fine. But again, as I mentioned, in practical domain, in the electronic circuits, this has other options that we ignored. And what are those other options that we never studied when we were studying the basic course of circuit theory? And these are the other options that may exist inside any given circuit. These options are highlighted in green. So we do say that since there is a voltage source, there should exist a current, and the current will flow for a short time. Another option that exists is that we are only relying on the output V out, which is equal to the source voltage, but we have also to take into account what is going to happen to the output voltage if the length of the wire is increased, or if there is some change in the shape of the wire, then what is going to be the output voltage, whether it will remain the same as the source voltage or it will be different. Another thing that we overlooked is what happens if we increase the frequency of the source. Right now I have just shown you that there is an AC source. I haven't given you exact value whether the source is in kilohertz or is it in megahertz or is it in gigahertz. Is it increased or is it decreased, or it is just in hertz like we have for most of the electronic or electrical components or the appliances which obtain or operate at 60 hertz. So we have to look into these three new possibilities highlighted in green and see what is going to be the effect at the output once these three things are taken into account. And these are the three things which are not discussed in circuit theory course. Rather, we are faced with these three problems, and this is addressed by the electromagnetic course, and that we are going to look into this course as well. So let us look into these three things one by one, the green ones. The first being that we cannot say that the current is 0 across the circuit. there is going to exist a small current. So for example, I'll redraw the circuit over here. If we have a voltage source, this is the switch, and these are the terminals, the output terminals. So if the switch is closed at time equals to 0, and this is an AC voltage source, we know whenever there is a potential difference, the voltage is going to generate a current. This current will come to this switch, and at time is equal to 0, then the current will move forward. So we do believe that circuit theory says that the current should be 0 because there is no path over here, but we want to understand what happens to the current which is produced by this source, or which is being constantly produced by this source. So we say that this current which exists over here for a short amount of time is what we call as a transient current. So in reality, the current exists, and this is tackled by the electromagnetic field theory, which we are going to study in detail in the coming chapters. So just to give you a hint, what is this transient current? So you may compare this flow of current or a transient current with the first order elements or the RL and RC circuits. So if you remember, when we talked about these storage elements, inductors and capacitors, we said that initially this is the condition for the inductor and this was the condition for the capacitor. So if we have an RL circuit, we know that initial current is something which is stored previously, and this was the transient current. So here is a graph of this transient current, which is shown with respect to time on the horizontal axis and the behavior of the current on the vertical or the y-axis. So we can see that the certain amount of time when the energy is stored in the form of current in inductor and voltage in capacitor. So we can see this is the transient behavior, and this is the amount of current which is available in the initial condition settings as per the equation shown over here. And after certain time constant, we say after, let's say, 5 tau, which was the ideal time constant, this transient behavior becomes a steady state current. So this portion is the steady state current, which means we generate a constant amount of fixed current after certain time constant. So we move from the transient to the steady state response. So our understanding is that the short amount of time the current is available, its behavior is the same as that of the transient portion of the current. So this is something that we in the electromagnetic field theory is going to consider, which we have talked about in the circuit analysis in terms of the RL and RC circuit, but the same behavior is experienced for the current which is being generated by the voltage source, and this is the current that is going to exist by the voltage source for a short time. So this is what the transient current is, and in the coming chapters we are going to talk about this thoroughly. Another thing that exists for the given circuit, and this is the circuit that we are talking about. So we have discussed about the transient. Now what happens to this length of the wire in terms of if the length is increased, and what happens if the shape of the wire is changed? So let us look into that concept as well. So what happens if we bend the wire? So in circuit theory, we say we don't care what happens to the shape of the wire or how long is the wire in terms of length. We always get the output as the source voltage. But we know in practical scenarios, whenever the shape of the wire is increased in terms of its length, or if there is some deformation in the wire, the output voltage will not be the same. Rather, the output voltage might decrease, or it might become equal to 0. Let's say if we go to the lab and consider connecting a resistor and an oscilloscope and see the behavior, we will see that the voltage becomes 0. So this means that if we change the wire or we introduce a certain bend in the wire, then the output is going to be affected, and this is thoroughly studied by the electromagnetic field domain and not the circuit theory. Similarly, if we increase the frequency, then what is going to happen? The third point, if we increase the frequency, what is going to happen? So this is again answered by electromagnetic field theory, and which we are going to study, is if we increase or decrease the frequency. Let's say if we lower the frequency, the source frequency, we see that the wire behaves as an inductor, which means now these characteristics will be dependent upon di by dt. So this is the change that we are going to have. So this is the inductor's behavior. Similarly, if we increase the frequency, it is going to behave as a transmission line. So what is a transmission line? We are going to look into that as well. This is basically we want to match the input power, or in terms of the input impedance, to the output impedance. So if we increase the frequency or decrease it, the behavior of the line or the wire is also affected in terms of it acting as an inductor for low frequency, and if the frequency is increased, it behaves as a transmission line. So these are the things which will be answered in the coming lectures, and this is the beauty of EMT, which helps us get solution to these. Finally, what happens if we keep on increasing the length of the wire? Obviously, circuit theory tells us we are not concerned about increasing the length of the wire, but it is an important factor to keep in mind. And what happens is, if we increase the length of the wire, we may get a lag of the signal received at the output. For example, if signal A is something which we transmitted, and if we keep on increasing the length, the output might get delayed, and this is known as a 90-degree phase shift in terms of its phase, or it's a lag or a leading problem. So here in this example, A is leading B because A's peak is appearing first compared to the B's peak in terms of its time. Similarly, the signal B might lead and A might lag at the output of the signal. Similarly, the waves might get a phase difference of 180 degree at the output of any system, and sometimes the phase will match each other. Again, how they are going to match or overlap, these are the different phase phenomena which we are going to study. But again, the idea is length of the wire has to be nominal. Normally we keep it as lambda. At best, we don't go beyond that, but we will understand this in the coming lectures, that this plays an important concept, and all these things will be mathematically calculated in terms of these three equations, in terms of the velocity of the wire, which depends upon its angular frequency or wavelength, the propagation delay, how we find the wavelength, and what is the relationship between wavelength and frequency. So just to give you a hint, we are going to study this, that the voltages and currents that propagate in a transmission line or a wire will be dealt with as a time varying element rather than a single particle. So these things are calculated in terms of the delays or the time delays, if the length of the wire is increased or decreased, and all these things are calculated in terms of its phase shift. So this is the beauty of electromagnetic field theory, where we can understand the limitations which we saw over here. So just to summarize, the limitations which we saw in terms of circuit theory represented in yellow are overcome by the solutions provided by EMT, and for all these three things highlighted in green. Finally, to summarize what we are going to study in this course, or what this course is all about, is we are going to start our analysis by understanding the vector calculus. Basically, we are going to understand how the signals are propagating in free space by considering them as a vector form. Then we are going to understand what are the Maxwell's equations that govern the joining of electricity with magnetism. So these are the four elegant equations in the differential form and the integral form which we are going to understand. And finally, we are going to see at the atomic level the charges in the electric and magnetic domain, and how the electric and magnetic charges are combined to generate an electromagnetic signal. Later on, once the course is understood and you are interested, then I can upload the lecture series for the advanced level EMT. So these three things are in the advanced EMT courses, where we are going to understand the working of the transmission line, the waveguides, and how the electromagnetic simulations are utilized based on these Maxwell's equations. So all in all, this course will be on this section, second section, and the combination of these three things. Later ones are for the advanced level of electromagnetic field theory. And that is all for today's lecture, where we summarized the course, where I gave the introduction about the course and what are the elements that we are going to utilize. Thank you for attending this lecture. See you in the next lecture series.